are in dark with no light, the first thing that we look around is a torchlight. In our day-to-day life, a torchlight has been very handy and useful for different purposes. The powering system for a portable torchlight is nothing but a simple battery. Likewise, we come across many portable electric devices, which almost every device has one thing in common: the powering system. Batteries of different specifications are used for powering many devices. Let's dive deep into the simple but fascinating physics of a cell or battery. A simple device to maintain an electric current in a circuit is called an electric cell. It's an electrochemical device which converts chemical energy into electrical energy. As seen in the figure, it has two terminals, positive terminal and negative terminal. When the cell is connected to a circuit, the circuit gets completed and electrons can start flowing, thus electric current flow occurs. Now let us look at the basic construction of the electrolytic cell. A basic electrolytic cell will have two electrodes, the positive electrode, which is the anode, and the negative electrode, which is the cathode. These electrodes are immersed in an electrolyte solution. Electrolytic cells are the electrochemical cells that can be used for the electrolysis of certain compounds. The electrolyte is the medium for the transfer of electrons between the cathode and the anode. When dipped in solution, the electrodes will exchange charges with the electrolyte. Due to this charge difference, the positive electrode will have a potential difference of V plus with the electrolyte, while the negative electrode will have a potential difference of V minus with the electrolyte. During the absence of the current, the electrolyte will have same potential throughout, and the potential difference between the electrodes will be V plus minus V minus. This difference in the electrodes is called the electromotive force, which is the driving force for the movement of electrons. If we look at the circuit in the electrolytic cell, the current in the circuit is flowing through the resistance from C to D. Clearly, across the electrolyte, the same current flows through the electrolyte from the negative terminal to the positive terminal, whereas through the resistance, it flows from P to N. So, the current through the cell is the opposite direction to that of the external circuit. This there offers a hindrance to the flow of the current. Internal resistance is the opposition to the flow of the current by the cells, and that is denoted by small r. The relation between the internal resistance and the EMF of a cell is given by E equals I times R plus R, where E is the EMF of the cell, I is the current passing through, and small r is the internal resistance, whereas capital R is the load resistance. On rearranging, we get E equals IR plus IR, or we can write E as V plus IR. Here V is the terminal potential difference when the current I is flowing through the resistance. In practical calculations, internal resistance of cells in the circuit may be neglected when the current I is such that E is much greater than IR. The actual values of the internal resistance of cells will vary from cell to cell. We also observe that since V is the potential difference across R, we have from Ohm's law as V equals IR. Thus we get the current flowing as I equals E divided by R plus R. Now let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.